Okay, we are back for, oh, I erased it. AP practice problems on the FTC, the final page, page 4. This page is significantly harder, I think, than the other 3 pages, but also maybe less abstract because we are talking about an object which is moving. I find it to be more difficult because I think there's somehow more that we have to say to justify our conclusions. Anyway, we begin. I'm not going to write down the full description of the problem because you have it in front of you, but you're given some graph. And I think what makes this problem particularly hard is that the graph for the first time is not one you are either given an explicit formula for, or nor is it sort of lines and semicircles for which you can calculate the areas. And so they sort of have to tell you what these areas are. And they do that right now. They say, a particle moves along the x-axis so that its velocity at time t is given by a differentiable function v whose graph is shown above. Okay, so we have some object, it's moving along the x-axis. So this is one-dimensional motion or rectilinear motion. So this is the thing that we did back at the beginning of April. And okay, so for this object, which is moving along a number line, we are told what the velocity is, and we're not exactly told it, but we're given a graph of the velocity. So this is a graph of the velocity, and we're told that this function is differentiable, this v function. So there are no crazy kind of jumps or anything like that. Of course, to the naked eye there aren't, but anyway. What else? The velocity is 0 at t equals 0, 3, and 5. Okay, that's what the picture is telling us, but we need to know this, so it's just saying, hey, there are 3 places where the velocity is 0. At 0, at 3, and 5. Okay, the graph has horizontal tangents at t equals 1 and t equals 4. Right, so that's a strange way of telling us, okay, there's a horizontal tangent at t equals 1, and there is a horizontal tangent at t equals 4. That means that's where the derivative is 0, so that's where the acceleration is 0. Or maybe that's just another way of telling us that, once again, trust your eyes, this velocity is decreasing until we get to 1, increasing until we get to 4, and then decreasing again from 4 to 6. I think that's the takeaway there. Finally, they tell us that the areas of the regions bounded by the t-axis and the graph of v on the intervals 0, 3, 3, 5, and 5, 6 are 8, 3, and 2 respectively. In other words, this whole sort of region has like area 8. This region has area 3, I'm going to erase these lines, and this region has area 2. Okay, and I think there's one more piece of information. This is the t-axis, and then the last piece of information to tell us is that at time t equals 0, the particle is at x equals 2. So at t equals 0, the thing is we're at x equals 2. That is also a thing given to us in the problem. Okay, sorry, negative 2. Negative 2. Shot. Okay, so maybe this is not so hard to figure out what's going on. Let's see, should we discuss or should we just begin? Maybe we just begin. Part A. Let's go. When is the, and maybe we'll do it something like this. Go across. Okay. When is the part A? Find both the time and position of the particle when the particle is farthest to the left. Okay, when is the particle farthest to the left? Alright, well, I think it's convenient here to create a new function to represent the position of the particle at time t. So let's just do that. I think you have to introduce that. Let s of t be the position of the object at time t. And okay, what do I know about this position function? Well, I know that s of 0 is negative 2. And let's just compute sort of everything else, right? Yeah, I mean, let's just do it, right? So maybe this is not that hard, because here I am, but once again, position function not depicted. This is the velocity function we're looking at, but I'm being told that at time 0 the position is -2. Let's just compute the position at all other times. Well, what is the position at time 3, for example? Well, in order to, if I know the position at time 0 and I want the position at time 3, it's going to be just the position at time 0 plus the integral from 0 to 3 of the velocity. So this is actually maybe not so different from the previous problems that we were doing. If you want to know the change in position, you just take the integral of the rate at which the position is changing, and by definition that's just velocity. So, so this is, well, s of 0 is -2, and the integral from 0 to 3 is -8. And so in fact, the position is -10 at time 3. Alright, what's the position at time 5? Maybe I care about this, maybe I don't, but let's just, I haven't really begun answering problem part A yet, I'm just doing some calculations. What's the position at time 5? Well, okay, if I knew the position at time 3 was -10, then the position at time 5 is just going to be the position at, the position at time 3 plus the integral from 3 to 5 of the velocity. Once again, the integral of the velocity gives you the displacement, the change in position. This integral was -8, that's why the change in the position was -8, and we went from -2 to -10. Which also makes sense. When the velocity is negative, we know we're moving to the left. Now, on the interval from 3 to 5, the velocity is positive, and so we're moving to the right. And so this s of 3, which is -10, is added to the change in position, which is just going to be 3, because that integral is 3. And so what we get is 7. Okay, and finally, what is s of 6? Well, it's going to be s of 5 plus the change from in the position from 5 to 6, which is just the integral of the velocity, and that is which is -2. And so we were at position 7, and now we add -2 or subtract 2, same thing. Because the object was moving to the left now. Velocity is negative, the object is moving to the left. And what we get is 5. Okay, and I sort of can't resist. Have I messed that up? -2, -10. Sorry, that should be -7. Sorry. And that's why... Oh my gosh, I was at -2, then I went back 8 to -10, then I went forward 3 to -7, then I went back 2 to -5. Why is that wrong? Oh my gosh. That's -2 plus -8 plus 3 minus 2, -11. No, it's just -9. Sorry, yeah, good. Yeah. It was 2, then -10, then -7, then -9 again. Good, good, good. Okay. Well, now maybe I'll just make a quick graph of position. I think this is maybe helpful over time. Where put some thought into this. So, what is my position? It's almost all going to be negative. In fact, here's -2, here's -10, here's -9, and here's -7. And I start at -2. This is position versus time. And here's where I am at 6. Here's 5. Here's and here's 3 or whatever. Okay. Sorry, having so much trouble with this. Okay. So I start here at -2, then by the time I get to 3, I'm down here at -10, and then it's -7, and then we're back down here at -9. Okay, let's begin to actually enter part A. Amen. Find both the time and position of the particle when the particle is farthest to the left. Justify your answer. Okay, unfortunately, justify your answer means we really need to explain in words everything. And so, okay, basically, so here we go. The position is farthest to the left when S of t is minimum on the interval 0, 6. In other words, this problem of finding the position farthest to the left is equivalent to just finding the minimum or the location of the minimum of the position function. And what is the minimum of the position function? Well, S of t is a minimum at the endpoints or at a critical point. And a critical point is when S prime equals 0. But that's equivalent to when v is 0, and we have just tested all the critical points. Okay, so by testing them all above, that is in fact what we did above. We just tested the value, we just computed the position function at every critical point. In other words, where the position function is, where the derivative of the position function is 0, in other words, where the velocity is 0. Okay, when S prime is 0, by testing them all above, we see that S of 3 equals -10 is minimum. Boom. Done. That to me is good. So the object is farthest to the left at time 3, and the actual position is -10. And this of course makes sense, right? The object starts, and then since the velocity is negative, we're going backwards. We end up really far to the left. How far to the left? 8 farther to the left than where we started, which is -10, and then we just never make that back up again, right? Because we move 3 to the right and then 2 back. But the full justification of this using calculus is that the minimum of the position function must occur at 0, at 6, or at a critical point where basically at a relative extremum, and by testing okay, we're done. What else? Part B. Okay, this part B I think is just crazy hard. Part B says, for how many values of t is the particle at x equals -8? Okay, first of all, what's just the answer to this problem? Well, the answer to this problem is, look, we made this position function, right? But notice how it's just a bunch of dots at the moment. I start at position -2, and I end at position -10 at time 3. I can say something more about the position. Since the velocity is negative, another way of translating that into the language of calculus with respect to s, I can say that s is decreasing. So I don't know exactly what s is doing, but s is decreasing on the interval from 0 to 3. And then, since v is positive on the interval from 3 to 5, and v is just the derivative of s is increasing on the interval 3, 5. According to some function, I don't know what, it doesn't matter. And then, since my velocity is negative on the interval 5, 6, it means that s prime is negative, which means that s is decreasing. And therefore, this is not accurate, but at least correct with respect to these points, and also whether the function is increasing or decreasing. This is a correct graph of s. And so now comes this sort of awkward question, how many values of t is the particle at x equals -8? Explain your reasoning. Okay, well, a picture now suffices to show that in fact there are going to be 3 times when the position is -8. Because the position was -2, it becomes -8 once by crossing on the way to being -10, again on the way back to being -7, and again on the way back to being -10, and no other times. Alright, and so a full justification of this, I think, is quite lengthy, and I just sort of don't feel like writing it. But there it is. And so maybe I'll just say something about this. Notice that they squeezed into this problem that v is differentiable. So maybe we want to throw in some line since v is differentiable, then s. Okay, how do I want to write this? Then s of t, which is after all just -2 plus the integral from 0 to t of v, is continuous. Is continuous on the interval 0, 6. In other words, if you have a differentiable function that's not doing any weird jumps or anything crazy, then the integral of that function will be a continuous function. Okay. In fact, well, okay. So I can apply the intermediate value theorem. That's essentially what I was doing here. So I'll just kind of write this in a little bit of a short way. By applying the intermediate value theorem to s three times on the interval 0, 3, the interval 3, 5, and the interval 5, 6, we see that s of t equals -8 at least 3 times. At least 3 times. Once on this interval, once on this interval, and once on this interval. And okay, now just saying something about this logic that I was discussing a minute ago. Since v is respectively on, okay, this is just getting ridiculous, on 0, 3, 3, 5, and 5, 6, v is negative, positive, and negative. S is decreasing, increasing, and decreasing on those intervals. And the reason why I mention this is because in fact, s of t equals -8 exactly 3 times. And I'll just stop there. Okay, because I didn't use the J-justify word, I don't feel pressure to explicitly write every single thing out, but I think you understand the logic, right? The intermediate value theorem says that if s is -2, and then later s is -10, then there must be a place where s is -8. But I can say something more. I can say that there's only going to be once on that interval at which s is -8, because in fact s prime is negative for that entire interval, and so it's decreasing. Okay. A true proof of this or something would require you to say something crazy like, well, I won't do it. I'll stop there. Okay. Good. I hope that all makes sense. I'm going to squeeze in the rest of this right now. Part C says, on the interval 2, 3, is the speed of the particle increasing or decreasing? Give a reason for your answer, which is kind of a vague prompt, but you just got to kind of explain what's going on. Well, what is happening on the interval 2, 3? Here's 2. What's happening to the velocity? Well, the velocity is getting bigger. But does that mean we are speeding up? No, because the velocity is negative and increasing, but increasing in this case means becoming less negative. And so in fact the speed, as measured by the size of the velocity, is going down. And that's really all you have to write, right? On the interval 2, 3, v is negative and increasing. And we're just stating that's by inspection, right? We're just looking at the graph, and we're seeing that the graph is increasing on the interval 2, 3. V is. So if the velocity is negative and increasing, then the speed, which is after all just the absolute value of the velocity, is decreasing, and the object is slowing down. The object is slowing down. Okay, good. Finally, part D says, during what time intervals, if any, is the acceleration of the particle negative? The acceleration will be negative when v prime is negative. And this is v, so we need only look at the graph of v and to see when its derivative is negative. And its derivative is negative when it's decreasing. When is it decreasing? On 0, 1 and on 4, 6. So now you just say, by inspection, v is decreasing on the interval 0, 1 and 4, 6. So v prime is negative, so the acceleration is negative on 0, 1 and 4, 6. Hopefully I did that right. Yeah. Okay, good. I hope you see that this is sort of bringing together everything we've learned this whole course. How long did that take? Terrible. Goodbye.